Hello my dear students, welcome back to the session. Uh, let's look at, in this particular session, some important problems. We call them special problems. I'll tell you why we call them special problems. Okay, because in GATE, some different varieties of problems are coming. Okay, if you are really good at concepts, you can answer any question that you come across. Okay, this I strongly believe in. And I always tell you also the same thing, that you try to be master in the fundamentals first. And you always try to generalize the problem. Okay, don't remember one particular problem, because that same problem may not come in the exam. Understand? Okay, that is why you can't remember or by heart that problem. You have to remember always the concept behind that. Okay, so now let us once again recollect the initial conditions procedure what we actually discussed. Okay, in the beginning sessions of the transient analysis. The first topic I discussed, initial conditions. So what was the step-by-step approach that we actually applied to find the initial conditions? The first step was, first you construct T equal to 0 minus equivalent and find current through the inductor and voltage across the capacitor. The second step was, okay, and in this case, suppose if you look at the question, in the question is asking what is the current through the inductor at T equal to 0 plus, okay, T equal to 0 plus, or what is the voltage across the capacitor at T equal to 0 plus, probably you can get the answer here itself. Yes or no? Because IL of 0 plus is equal to what? IL of 0 minus, and VC of 0 plus is equal to what? VC of 0 minus. That's it. If the question is other than, current through the inductor, that means IR of 0 plus or VR of 0 plus, VL of 0 plus and IC of 0 plus. For this particular calculation, I told you already to go to what? Step 2. Yes, in step 2, what shall we do actually here? You construct T equal to 0 plus equivalent circuit, and then you find whatever you want. I also told you the first derivative terms can also be determined. dIL of 0 plus by dt, nothing but VL of 0 plus by L. Okay, that we find VL of 0 plus from step 2 only, and also dVC of 0 plus by dt, which is nothing but what? IC of 0 plus by C. Okay, all these quantities can be determined from what? Step 2. So therefore, step 1 and step 2 are very clear. In first step, you are going to find the T equal to 0 minus equivalent circuit and find what is the current through the inductor, what is the voltage across the capacitor. And if the question is IL of 0 plus, VC of 0 plus, we immediately conclude that IL of 0 plus is equal to IL of 0 minus, VC of 0 plus is equal to VC of 0 minus. This is what the normal procedure. Yes or no, all of you? But on what basis you concluded that IL of 0 plus is equal to IL of 0 minus? VC of 0 plus is equal to VC of 0 minus. You have assumed that voltage across the inductor is finite. Current through the capacitor is finite. But what is the guarantee? What is the guarantee that voltage across the inductor is finite and current through the capacitor is finite? Did you check that in the previous problems? We did not check at all. We did not check whether voltage across the inductor is finite or not. We did not check whether current through the capacitor is finite or infinite. Without bothering whether voltage across the inductor or current through the capacitor are finite or infinite, we have just concluded. Don't worry, they are all finite, no doubt in that. But sometimes you may get infinite. Then what will you do? That means before you conclude IL of 0 plus is equal to IL of 0 minus, better you check whether okay, current through capacitor is finite or infinite. Infinite is nothing but ideal impulse. Voltage across the inductor is finite or infinite. That is nothing but ideal impulse. If you check, if they are finite, then you conclude IL of 0 plus is equal to IL of 0 minus, VC of 0 plus is equal to VC of 0 minus. If they are not finite, that means ideal impulse, then definitely IL of 0 plus is not equal to IL of 0 minus. VC of 0 plus is not equal to VC of 0 minus. You understand all of you? Okay. That means without knowing whether voltage across the inductor and capacitor, or current through the capacitor, we cannot conclude these two. Now onwards, you must be careful. I should have told you the same thing in the initial class itself, but you will get confused. That is why I did not discuss that. Now you got complete maturity in the initial conditions calculations. You got complete idea. Now we can make some changes in our approach. Okay. Now let us generalize the problem. Whenever the problem is given on 0 plus conditions, now let us draw the important steps, the final steps we can say otherwise. Okay. So what is the first step that you can do is, you construct T equal to 0 minus equivalent as usual, no doubt. And you also construct T equal to 0 plus. Find IL of 0 minus and VC of 0 minus, no doubt. Now don't conclude without constructing T equal to 0 plus. That means construct T equal to 0 minus, find current through inductor, voltage across capacitor. Also construct T equal to 0 plus equivalent circuit. Then you verify whether current through the capacitor is finite or infinite, voltage across the inductor is finite or infinite. Then only you will come to know. Understand all of you? Okay. Now at step two, okay, you check whether VL of, okay, whether VL is finite or infinite. Finite or infinite. IC is finite or infinite. Then you come to conclusion. Understand all of you? Okay. I'll give you, based on this particular observation, one problem, then you will understand it clearly. Okay. So what is the first step? Construct T equal to 0 minus. What is the second step? Construct T equal to 0 plus. In the second step, you are observing whether VL is finite or infinite, IC is finite or infinite. Then based on that, I'll conclude, or I'll try to answer the question. Okay. So first one is the question number 1 in the classroom workbook, in the special problems on transient analysis. Okay. Find VC1 of 0 plus and VC2 of 0 plus. Find VC1 of 0 plus and VC2 of 0 plus. Look at this problem. It's a very interesting question. The switch K closed at T equal to 0 and the voltage is V0. Okay. Or V, let us say. V or V0 doesn't matter. Okay. Yeah. In the problem, it is given V0. You can take it V0. Not a problem. This value is R, capital R. Now what is asking here? V1 of 0 plus and V2 of 0 plus. Okay. VC1 of 0 plus and VC2 of 0 plus. What is VC1? Voltage across the capacitor. What is VC2? Voltage across the capacitor. At T equal to 0 plus is asking. We know that according to the older procedure, okay, the first procedure what we followed, we understand that if you find VC1 of 0 minus, VC2 of 0 minus, there ends the matter. Yes or no, all of you? But look at this, all of you. In the first step, T equal to 0 minus equivalent, I know that VC1 of 0 minus is how much? 0, because the switch is open. And uncharged capacitors, he did not mention any charging, okay, in the capacitors. And VC2 of 0 minus is also what? 0. Yes or no? Usually we conclude from this particular stage only, in this stage only, we conclude usually VC1 of 0 plus is equal to VC1 of 0 minus is equal to 0. Similarly, VC2 of 0 plus is also 0. Okay, but that may be wrong answer. We don't know whether current through capacitor is finite or infinite. We don't know. Without knowing that, how can I conclude that? That is why I told you to construct what? T equal to 0 plus. Don't conclude here. Before you conclude, better you go for T equal to 0 plus. Then you observe whether current through capacitor is finite or infinite. Based on that, we'll conclude. Look at this. At T equal to 0 plus, this equivalent depends on what? These values only. So what you get? Switch is closed. Capacitor is acting like short circuit as it is 0 volts. Resistor remain resistor. Yes or no? And this capacitor voltage is 0. Therefore, short circuit. Plus minus V0. This is C1. This is C2. This is capital R. Now closely observe this network. You will understand a very interesting point, that This can be neglected because it is shorted. Now C1, C2 are acting like short circuit. The voltage source got shorted. The voltage source got shorted. Kirchhoff's voltage law got violated. The current is found to be what? Infinite. You understand all of you, okay? Kirchhoff's voltage law got violated and the current through this particular circuit. You know that wherever Kirchhoff's voltage law is not satisfied, there definitely infinite current results. We have learnt this concept only in the first class itself. Very beginning class. The fundamental concept it is. Now look at this, all of you. This infinite current is flowing in which time or which duration? As soon as you close the switch. Before closing the switch, t equal to 0 minus, the current was found to be 0. And upon closing the switch, the current was found to be infinite. Now tell me, this difference, the difference you find here, I1 and I2, okay? I1 and I2, that is nothing but what? I2 minus I1 is nothing but infinity. In the duration of 0 plus and 0 minus, nothing but what? Infinite current, okay? Infinite current in 0 time is nothing but what? Ideal impulse. Ideal impulse. When ideal impulse current is flowing through each capacitor, okay, therefore, when ideal impulse current is flowing through each capacitor, therefore, Vc1 of 0 plus is not equal to Vc1 of 0 minus. Yes or no? Is not equal to Vc1 of 0 minus. Similarly, Vc2 of 0 plus is not equal to Vc2 of 0 minus. You understand, all of you? Okay, if you do not know this concept, you would have concluded, okay, in the first step itself that Vc1 of 0 plus is 0. Vc2 of 0 plus is also 0, but they are not 0. Why they are not 0? Because we observed that current flowing through each capacitor is found to be ideal impulse. Okay, therefore this condition no more, okay, exists, or this condition is no more valid. Understand, all of you? Okay, so therefore you must be very carefully observe this kind of problems. That is why I put a heading, special problems in transient analysis. Understand, all of you? Okay, special problems in transient analysis. So when I know that they are not equal, then I must calculate separately what is that Vc1 of 0 plus. Yes or no? Generally when IR of 0 plus is asked, what shall we do? We go for step 2 only. Why? Because IR of 0 plus is not equal to IR of 0 minus. When they are not equal, I have to find, especially by using t equal to 0 plus condition only. Yes or no, all of you? Okay. Now look at this. It's a very interesting point to be observed. This is very important point here. And after that, now you can see, as soon as you close the switch, listen to me carefully. Listen to me carefully here. As soon as you close the switch, now ideal impulse current is flowing through the circuit, that is nothing but capacitor 1, capacitor 2. What will happen? This ideal impulse current will force the charge deposited on each conducting plate of each capacitor here, okay, to some value. Because what was the charge initially here? QC1 of 0 minus is how much? 0. QC2 of 0 minus is how much? 0. Yes or no, all of you? 0. Now, because of this ideal impulse current, okay, because of this ideal impulse current when it is passing through it, okay, now because of this, the QC1 of 0, okay, minus whatever that charge is there on the capacitor, okay, it will be moving to some value QC2 of 0 plus will also move to some value, because now this ideal impulse current will force the charge on each capacitor to change from its initial value to some other value. You understand, all of you? Usually the charge of the capacitor may not change instantaneously, provided current through the capacitor is finite. If current through the capacitor is ideal impulse, the charge in the capacitor may change instantaneously. Initially it is 0. Now it is not 0 at t equal to 0 plus, it is something else. When charge is changing to some other value, then voltage will also change to some other value. But which value it will change to? This ideal impulse will force the charge to change to some value in such a way that Kirchhoff's voltage law is satisfied. You understand all of you, okay? Kirchhoff's voltage law is satisfied. Now the ideal impulse current will force the charge deposited on each capacitor in an amount such a way that Kirchhoff's voltage law is satisfied. It's a very, very important point to be observed. Okay, that means KVL must be satisfied. Where is that KVL? Actually, here you are supposed to apply here. This R is neglected. C1, C2 will be coming in series, and KVL must be satisfied here. To satisfy KVL, okay, some value in order to satisfy Kirchhoff's voltage law. To satisfy KVL, what is VC1 of 0 plus Nana? Because C1 and C2 are in series now. Yes or no? They are in series because R is neglected. So VC1 of 0 plus is equal to opposite, that is C2 by C1 plus C2 into V0. And VC2 of 0 plus is opposite, that is C1 by C1 plus C2 into V0. That's nothing but, you're going to get the VC1 of 0 plus and VC2 of 0 plus, these values. Understand all of you, okay? So I think you understand the concept, okay, here clearly. Now, what is the conclusion that you want to give? Whenever initial conditions are asked, now we are confused whether we are doing correct answer, correct procedure or not, whether we are following correct procedure or not, right? So what you do is simple procedure, I'll tell you. First you construct t equal to 0 minus, find IL of 0 minus, VC of 0 minus. Then you construct t equal to 0 plus. In that equivalent circuit, check whether current through capacitor is finite or not. Voltage across the inductor is finite or not. Based on that, you conclude. Understand all of you, okay? So please note down. I'll give you some important points to be noted down, okay? Note. What you do is, first you note this and this and this, and then I'll give you some points. Okay? It's very clear that infinite current is passing in zero time. Yes or no? Point. Now, this ideal impulse current will force the charge deposited on each capacitor. Will force the charge deposited on each capacitor to change will force the charge deposited on each capacitor to change in an amount or else to change from initial value to some value in such a way that KVL is satisfied. Therefore, as C1, C2 are in series, neglecting R1, R value, okay? So, to satisfy KVL, this voltage must be divided according to the capacitance values, yes or no? So, VC1 of 0 plus is equal to C2 by C1 plus C2 into V0. VC2 of 0 plus is equal to C1 by C1 plus C2 into V0. Before that, you can also write, okay, QC1 of 0 minus is 0, QC2 of 0 minus is 0. Ideal impulse current will force now to some other value. in 0 time, 0 minus to 0 plus, the VC1 of 0 plus will be some other value, because we know that QC1 of 0 plus is not equal to QC1 of 0 minus, and QC2 of 0 plus is not equal to QC2 of 0 minus. Yes or no? Therefore it will force the charge to from 0 to some other value in such a way that K will is satisfied. This is a very, very important point to be observed. Okay, very interesting points. So I think you have noted on this also, right? Let me take another problem. Any problem is given now onwards, let us proceed in this way only. This is I0, question number 2 in the classroom workbook. This is I0 or I, okay? Yeah, I. And the switch is open at t equal to 0, L1 and L2. This is L1, this is L2. The question is, what is IL1 of 0 plus and IL2 of 0 plus? What is IL1 of 0 plus and what is IL2 of 0 plus? Okay. So now look at that. Whenever 0 plus conditions are asked, now let us standardize the procedure. What is the first step? Construct t equal to 0 minus. Yes or no? Construct t equal to 0 minus. So let's construct t equal to 0 minus. What is the switch position, Anna, in that network? The switch position is what? Closed initially. So can you charge inductor by keeping a short circuit across it? No, not possible. Therefore, the IL1 of 0 minus is what? 0. Obviously, IL2 of 0 minus is also 0. So the current flowing through L1 and L2 at t equal to 0 minus was found to be what? 0. IL1 of 0 minus is 0. IL2 of 0 minus is also 0. This is at t equal to 0 minus. I told you before you conclude IL of 0 plus is equal to 0 minus, okay, better you go for what? T equal to 0 plus. Let us draw the equivalent here. What's happening? This switch is open condition, right? Okay. The inductor is, current through the inductor was found to be 0, IL2, therefore open circuit. This is an inductor, don't forget, L2. And here is an inductor, L1. This is capital R and capital I. Understand all of you, okay? Now, if you observe this is open circuit, this is open circuit, this is open circuit. Current source is opened completely. When current source is open, you look at this, I is flowing up to this point, but no current is leaving, only I is entering, but no other current is leaving. That means here, the Kirchhoff's current law got violated. Whenever Kirchhoff's current law gets violated, the voltage becomes what? Infinity. Yes or no, all of you? The voltage across the current source infinity, nothing but voltage across this inductor is also infinity. If the voltage across this L2 is infinity, since there is no current flowing here, I can neglect this R, the same voltage will appear across L1 or not? Yes or no? That means L1 and L2 both are experiencing infinite voltage. And this infinite voltage is appearing across each inductor in the duration of what? 0 minus 0 plus. Nothing but what? Nothing but what? Ideal impulse. When ideal impulse voltage is appearing, then current through the inductor may change or may not change. May change instantaneously. Therefore, look at this now. Look at this. IL, what is this actually here? You have written clearly. KCL is violated. When KCL is violated, as a result, okay, you get IL1 of 0 plus is not equal to IL1 of 0 minus. And IL2 of 0 plus is not equal to IL2 of 0 minus. Clear all of you? Okay. Now, what will happen here is, when current may not change instantaneously, the same thing you can apply even flux linking with the first coil also may not change instantaneously, or may change instantaneously. Okay. Then phi 2 of 0 plus is not equal to phi 2 of 0 minus. That's it. Okay. So what's happening here? This ideal impulse voltage will force the flux to change from its initial value. What was the initial value actually here? Okay, phi 1 of 0 minus, phi 2 of 0 minus, both are 0 only. Now this ideal impulse voltage, whatever the impulse voltage is there, okay, this ideal impulse voltage will force the flux to change from its initial value to some value in order to satisfy Kirchhoff's current law. I hope you understand the point. Okay. Now, since this ideal impulse, now the ideal impulse voltage, right? Now, impulse voltage will force the flux of each inductor to change right on to change from initial value to some value such a way that KCL is satisfied. You understand all of you? Okay, just like in the previous case, the ideal impulse current will force the charge to change from initial value to some value. Okay, what is that some value? It is in order to satisfy Kirchhoff's voltage law in the previous case. Now it is in order to satisfy Kirchhoff's current law. So now you can observe that the L1 and L2, if you neglect this, L1 and L2, how they are connected? This is L2, right? L2 and L1 both are connected across each other. The parallel combination of L1 and L2 is supplied by what? The current I. Because I'm neglecting this. This is open circuit, this is neglected. Therefore, these two are connected across each other. Therefore, neglecting capital R, okay, L1 and L2 become parallel. Once they are in parallel, then you will understand IL1 of 0 plus opposite L2 by L1 plus L2 into capital I. IL2 of 0 plus, because I can go for the current division rule because I know the total current. Now KCL must be satisfied. That means current must be divided according to the inductance values. In accordance with the inductance values, okay, that is inversely proportional to the inductance values. L1 by L1 plus L2 into I. That's it. So these are the values of IL1 of 0 plus and IL2 of 0 plus. Most of the students will choose an answer 0 and 0 because they know that in the first step, current through the inductor they find and they may not change instantly. The standard statement they fix in the mind, they go for it. But I'm telling you, these are the special problems. You must be always careful. So step 2, you verify whether anywhere KCL, KVL getting violated or not. Understand? Okay. Please note down. Okay. I remove this part only. Please note down. So let's have a look at another important question here. Question number 3, classroom workbook, special problems in transient analysis. This question was asked in GATE. It's a very interesting question. Now you will understand the importance of the method that what we discussed. Okay. Yes. Now look at this. Okay, let me read the question first. I think all of you might have gone through that. Okay. Let me read it clearly. In the circuit shown below, all elements used are ideal. For t less than 0, S1 remain closed and S2 open. At t equal to 0, S1 is open and S2 is closed. If the voltage Vc2 across the capacitor C2 at t equal to 0 is 0, then the voltage across the capacitor combination at t equal to 0 plus will be, 4 options are given. Okay. So what is asking actually the capacitor combination at t equal to 0 plus. Okay, at t equal to 0 plus. The voltage across the capacitor combination at t equal to 0 plus will be. T equal to 0 plus means what? Actually this is closed for some time and then it is opened. Then at t equal to 0. Okay. This is happening. This is what according to the data given, I am just putting the directions of the switches. Okay, because first initially remain closed, S2 open. Then at t equal to 0, S1 is open, S2 is closed. Therefore, based on that, I can indicate the directions like this. So let us look at now the capacitor voltage combination. The combination of the capacitors you can see at t equal to 0 plus. Once the switch is closed, both are across each other. C1, C2. Yes or no? Now Vc1 of 0 plus is equal to what? Vc2 of 0 plus. You call it V of 0 plus. Now V of 0 plus is same as Vc1 of 0 plus and Vc2 of 0 plus. So let's find what is Vc1 of 0 plus or what is Vc2 of 0 plus. Okay, let's find that. At 0 plus conditions, if you want to find always a standard procedure, what is that? T equal to 0 minus conditions first. At t equal to 0 minus, what is Vc1 of 0 minus? What is that? 3 volts. Yes or no? Because it is getting charged. And Vc2 of 0 minus is 0 because it's uncharged capacity, as mentioned clearly. Even if it's not mentioning, we can understand, or default case we can take it 0 only. This is what the values. At t equal to 0 plus, okay, don't come to a conclusion immediately that Vc1 of 0 plus is equal to Vc2 of 0 plus, Vc1 of 0 minus. Vc2 of 0 plus is equal to Vc2 of 0 plus. No, don't come to such conclusion. I told you clearly, you construct t equal to 0 plus equivalent, then only you come to a conclusion. Now, what's happening? Switch is open. Yes or no, all of you? Okay, now what's happening here? This switch is, this particular capacitor is replaced by short circuit with a series capacitor model, with a voltage source with a series capacitor model. This is 3 volts. Switch is closed, right? Now this capacitor becomes again short circuit because the voltage is 0. Here it is 3 volts. Okay. This is C1. This is C2. That's it. Now it is clearly understand that this voltage source got shorted and KVL got violated, and this happens in the duration of 0 minus 0 plus. Therefore, current flowing through each capacitor is what? Infinity. You call it what? Ideal impulse current. You call it ideal impulse current. When ideal impulse current flows, therefore, Vc1 of 0 plus is not equal to Vc1 of 0 minus. Vc2 of 0 plus is not equal to Vc2 of 0 minus. That's it. Yes or no, all of you? When they're not equal, we are supposed to find those values. Yes or no, all of you? So what are those values? Let us see. Now this ideal impulse current will force the charge deposited on each capacitor, okay, will force the charge from initial value to change from initial value to some value. Which value? The value for which the Kirchhoff's voltage law is satisfied. So therefore, now to satisfy, okay, to satisfy KVL, look at this. Now this voltage must be divided between these two. Yes or no, all of you? Okay. Now what is Vc2 of 0 plus now? Because these two are in series, the voltage you can say this is Vc2 of 0 plus. Understand all of you? Okay. Now what is that value? C2, the C1 by C1 plus C2 into 3 volts. What is C1 actually? 1 by 1 plus 2 into 3, that is 1 volt. Understand all of you? Okay. What about VC1 of 0 plus? As I told you, both are same, but still would like to calculate. You know that the voltage across C1 is, now this is, let us say, since it is getting divided, now this particular voltage you are going to get, what is this actually here? V1 of 0 plus. See, this is not VC1. VC1 is total voltage. But what is this capacitor model voltage, or the voltage across the capacitor model in the equivalent circuit? You call it V1 of 0 plus. So therefore, this is V1 of 0 plus, nothing but what? C2 by C1 plus C2 into 3 volts. So you know that 2 by 2 plus 1, again this is 2 volts. But what is actually VC1 of 0 plus is the total voltage. Here it is the total voltage. This is VC1 of 0 plus. Understand? Minus plus 2 volts plus minus 3 volts. Algebraic sum will give you, this is minus 2 plus 3, again 1 volt. That means you got VC1 of 0 plus and VC2 of 0 plus, both are same or not? Yes, they are. And the capacitor combinations, that means he's asking actually here, what is the voltage between these two? VC of 0 plus. In fact, these two are same. VC of 0 plus is equal to VC1 of 0 plus is equal to VC2 of 0 plus. All are same. This is 1 volt. I hope you understand the point. This is how you are supposed to think and apply. Okay, so this problem was asked in GATE. So I think you understand the importance of the discussion what we had before discussing this problem. We had a lot of discussion on how to really proceed with the initial conditions. So now you feed the updated method in your mind to find 0 plus conditions. Okay, do that. Meanwhile, I just note down another problem. This was question number 3. And let's go with question number 4. You understand, all of you? Some people do the solution in a different procedure using S-domain approach. Yes, you can also do, because S-domain is a versatile approach. Let me do it also using S-domain approach. See, using S-domain approach, you find VC of t. Once you know VC of t, can't you find what is VC of 0 plus? See, if you have time response, you can find anything that you want. And this response you are finding for what? S-domain for what? T greater than 0. Then once you find VC of t for t greater than 0, you can find what is VC of 0 plus also. So let's construct what is the S-domain equivalent circuit. What does it tell me? 1 by S, 3 by S. This is what? 2 by S. He's asking what is VC of S. What is VC of S? VC of S. Okay, 2 by S by, because now this is Z2, this is Z1. So voltage across Z2 is nothing but Z2 by, yes or no? Z1 plus Z2 into total voltage 3 by S. Okay, that's it. Yes or no, all of you? So what do you get here? VC of S. What was the voltage actually here? Two by S. This is 1 by S. VC of 0 plus. I mean S domain equivalent for t greater than 0. S domain equivalent for t greater than 0 can be calculated, okay, here as 2 by S, that is, this is 2 by S by 3 by S into 3 by S. This both will get cancelled. Finally, you are left with what? 2 by S. Understand all of you? Okay, right. So once you know the VC of S, can't you find what is VC of T? L inverse of VC of S, nothing but what? Okay, this is 2 only, 2 volts. So what is VC of 0 plus? Is also 2 volts. But what you got actually here? 1 volt, right? So somewhere you have done a mistake. Where is that mistake? You can see the voltage. Actually here the calculation mistake is taken place. What was that actually? 1 by S, 1 by 2S. Yes or no? 1 by 2S. Right. So here 1 by 2S. This is what actually we are supposed to do. So I just made a small calculus mistake. Please correct it. Please correct it, all of you. Yeah, because we have written that capacitive reactance is what? 1 by Cs, right? So already 2 farad is there. 1 by Cs means 1 by 2S. So what do you get here? 1 by 2S means the 2S into S it gets cancelled here, and you can 1 by 2S by what do you get? 3S by 2S square into 3 by S. So SS get cancelled here, SS get cancelled, 2 also get cancelled. Okay, 3 get cancelled. So finally you are left with 1 by S. Yes. So VC of T is equal to L inverse of VC of S. Okay, what do you get here? Therefore 1 volt. That's it. So 1 volt VC of 0 plus, if you substitute here also you get what? 1 volt. You get what? 1 volt. That's it. Clear all of you? Okay. So this is how you are supposed to solve the problems. Okay. There is simple calculus mistake has been taken place. This is 1 by 2S, not 1 by 2 by S. Okay. Hope I think you have noted down this. One more problem I'll give you, which was asked in GATE. I'll give you one more problem. Please note down. Yes, you can also go for S-domain approach. Yes, you can also go for S-domain approach, but I'm telling you in the previous problems, if you go for S-domain approach, it will take a lot of time. If you know the concept, you can easily apply without taking much time. And you may not understand all the time, you cannot go for S-domain approach to find initial condition. That is not a good practice. To find initial condition, one must not go for S-domain approach, because you know that already it is a time-taking process. Okay. So now let's go with another question here. Fourth one, right? Fourth one. Read the question here. This was asked in IES, not in GATE. IES. In the circuit shown below, switch K is closed at t equal to 0. The circuit was initially relaxed. Which one of the following sources of V of t will produce maximum current at t equal to 0? Unit step, option A. Option B, unit impulse. Option C, unit ramp. Option D, unit step plus unit ramp. Very simple question. Okay. So circuit was initially relaxed and now you are closing the switch at t equal to 0. Now what could be the maximum current? When does it flow? When V of t is a step function, impulse, ramp, or step and impulse combination. Okay. Step and ramp combination. Okay. Look at this, all of you. First of all, if you take the first option, what is the first option actually? Unit step, right? B, unit impulse. C, unit ramp. D, what is the D actually given? Unit step plus ramp combination. Okay. Look at this, the current through the inductor, you know that IL of 0 plus is not equal to IL of 0 minus. You know that IL of 0 minus is how much? 0. So I of 0 minus, because already given here I of 0 minus I. Therefore, let me take I of 0 minus. So I of 0 minus is 0. Can you conclude immediately that I of 0 plus is equal to I of 0 minus without checking whether the inductor is experiencing impulse voltage or not? You cannot conclude. So in step 1, for t equal to 0 minus, you know that I of 0 minus is equal to 0. But in step 2, t equal to 0 plus, when you draw, when the switch is closed, okay, this voltage will appear across. This element will become what? Switch closed and resistor. And now this is what the voltage plus minus. Yes or no, all of you? This is an inductorial. Okay, this is R. Now, if it is a unit step is what? A finite voltage. When finite voltage is appearing across it, I of 0 plus is equal to what? I of 0 minus. So for this, you get the current is, okay, the current is what? 0 only. Because the current through the inductor may not change instantaneously. I of 0 minus is equal to 0. But when you take this one, okay, when unit impulse is given, current through the inductor may change or may not change? May change. Okay, therefore, I of 0 plus is not equal to I of 0 minus. It is not equal to means what? Definitely some other value will be there. But already the current flowing through the inductor t equal to 0 minus is 0. Now, other than 0 means what? Definitely greater than 0. Okay, so you are getting the current through the inductor when unit impulse is given, the current flowing through the inductor is definitely greater than 0. Now, when unit ramp is given, definitely I of 0 plus is equal to I of 0 minus. When unit step plus ramp is also given, I of 0 plus is equal to I of 0 minus. Only in one case, okay, I of 0 plus is not equal to I of 0 minus. That means the current is not 0. It is a non-zero value. Non-zero value is definitely greater than the 0 value. That means maximum current flows only when unit impulse is given. I think you understand the point. Okay. So, very interesting question that is. Question number 4. If IL of 0 minus is plus 1 ampere, then what is IL of 0 plus? Okay. A minus 1 ampere, B 1 ampere, C 0 ampere, D 2 ampere. Okay, you can write the point here. When unit impulse is applied, I of 0 plus is not equal to I of 0 minus. That means the current flowing through the inductor is not 0. Whereas when unit step ramp and unit step plus ramp is given, the current flowing through the inductor is 0. Therefore, the maximum current flows to the inductor when unit impulse input is given. Very simple. Now coming to the question number 4. Question number 4. If IL of 0 minus is equal to minus plus 1 ampere, what is IL of 0 plus? So he's asking 0 plus conditions. So in this case, when impulse is given, okay, when impulse is given, definitely IL of 0 plus is not equal to IL of 0 minus. So don't say it is again 1 ampere. It's very clear. Don't say IL of 0 plus is equal to IL of 0 minus. 1 ampere is readily available. Don't go for that option. Because unit, the impulse function is given here, definitely you have to find it separately. Now in this case, definitely, okay, you have to go for S-domain approach. There is no other opportunity here. Okay. So what is that S-domain? S-domain for t greater than 0. If you find IL of S, IL of t, then substitute t equal to 0. Nothing but IL of 0 plus. So what do you get here? 1 volt minus plus. What is this value? 1 volt, because 1 into 1, right? So what is this? F. So this is what actually IL of S. So what is IL of S here? 1 plus 1 by S, 2 by S. Therefore, IL of T is L inverse of IL of S. That is 2 amperes. That's it. When IL of T is 2 amperes, what is IL of 0 plus? Is also 2 amperes. Option D is correct. Option D is correct. So this is how you need to solve the problems, my dear students. Special problems. That's why I put special problems. Okay, this is the fifth problem or fourth problem. Yeah, this is the fifth problem. Okay, this is the fourth problem. This is the fifth problem. Okay. So all different varieties of problems we have come across. I'm telling you, you need to have a lot of practice. Otherwise, I'm sure that you cannot become master. Okay. So today's class, I mean, in this session is really important. Special problems in transient analysis is a very, very interesting topic. You go through any textbook, you may not find all these concepts I'm telling you. Okay, in the textbooks generally they may not go through the details of all these things. They may give you fundamentals, no doubt in that, but I have elaborated each and every point. So read that carefully once again and practice all the problems which I've explained. I'm sure that you will definitely become perfect in all these, okay, problems. So I stop the session here.